let's build on our knowledge of geometry and kind of help that guide us into the calculus aspect of finding area under a curve. So if I'm going to integrate, what I'm being asked to do is find the area under the curve, and kind of think about that word, right, in quotation marks, because it doesn't necessarily have to be curved. It could be linear. Okay, but the area under the curve, between the curve and the x-axis. So the idea here is, can I graph the line y equals 4? Okay, we're treating this as our function, right? This is f of x. So y equals 4 is going to be a horizontal line. So if I were to graph this, I would have a horizontal line at 4. To find the definite integral, what I'm being asked to do is find the area 1 to 6 between 1 and 6 under the purple line, under 4, between 4 and the x-axis. So we do have that x-axis as a boundary. Now, obviously, this is a rectangle. So what I'm looking at here is, how do I find the area of that shape? That is what integration, definite integration, is asking us to do. It's asking us to find that area. So if it's a rectangle, I'm going to use geometry to do that. So what we're going to do is we're going to use the width of 5, and that does come from that 6 minus 1, right? So 6 minus 1, the difference between the A and B, right? The definite integral pieces. The limits of integration, if you will. Right? And then obviously times 4, because that's the height. So the width, and you could call it a height, you could call it a length. It depends on kind of how your brain works. But obviously I'm dealing with 20. Now, that is 20 units squared, right? But I do not have a inches or a meters or a feet attached to that. So as long as it's an integral, we know that it's in units squared. We don't necessarily have to attach a unit unless it's an application problem. So let's look at another one. Not everything is a horizontal line. We could have the line x plus 2, right? Remember, this dx is representative of the variable, okay, that we are working with respect to x. This is the difference, saying that I'm going from x equals 1 to x equals 6. So here I'm going from x equals 1 to x equals 3. Okay, so that dx matters. It indicates the variable that I'm working with, right? But it doesn't necessarily have a unit measure. All right, so I'm going to go, I need to graph x plus 2. Well, I know what that looks like. So I'm going to go up 2. Right, and then I am going from 1 to 3. Go ahead and get a scale on here. Make sure everybody knows what's happening. And then I've got plus 2. I'm just going to go up 1 over 1. Up 1 over 1. Up 1 over 1. So there's my line. And my limits of integration are from 1 to 3. So I'm trying to find the area of that trapezoid. To find the area of the trapezoid, you could do a rectangle and a triangle, but we need to be comfortable with the area of a trapezoid. So it's going to be 1/2 base 1 plus base 2 times height. Okay, that is the area of a trapezoid. So that's what I'm going to set up. I'm going to do 1/2 base 1 plus base 2. Okay, this right here is your base 1. This is your base 2, because those are the pieces that are parallel to one another. So I'm going to have a height of 3 and a height of 5, right? That's 5 units. This is 3 units. So 3 plus 5 times height, and height is the distance from base to base, right? So this distance here, which is 3 minus 1, so that's 2. So this is, I'll go ahead and make a note of that. Height, distance from base to base. The parallel sides are considered to be the bases. All right. So just a little math here. We're going to end up with 8 representing the quote-unquote area under the curve. Yes, I recognize that it's a line. All right, but we're calling it area under the curve, and we're using geometry to get there. But this is the integral notation. So the integral from 1 to 3 of all of this is equal to 8. It represents that area.